All right. Good afternoon. Well, good evening. Welcome back. Let's see. I'm recording. Everything good. All right. We're going to get started now. Let's see. All right. So today we're going to begin with solving exponential and logarithmic equations by using the log properties and some of the exponential properties that we have seen in the past. And then we're going to move on to talk about some modeling with exponential and logarithmic functions. You've probably seen those before, like a doubling time, half-life, those kind of problems. And then I think that's going to cover a good amount of the material we need to talk about. All right, let's see. Double check, make sure everything's good. All right. Okay. All right, let me just quickly remind you that we're going to have a quiz today. It's going to be towards the end of the lecture, just like before, and I'll make sure I give you enough time. Let's see, I need to double check one more thing. Hold on. All right, let me stop sharing for a minute. Okay. All right. Share screen. Okay. All right. So quiz today, that's only going to cover 4.2 to 4.4. The properties with logs, they're not going to be on it. Excuse me. Sorry. But it will be on the next assessment. So quiz today, and also a reminder that we're going to have exam 2 on the following Monday, which is August 8th, I believe. All right. Any questions before we get started, including questions about the exam? Sorry, go ahead.
Hi, I did have a quick question about our previous homework 4.
Correct.
It was number 2. I don't know. Do you want me to pull it up?
Yeah, or you can just tell me. Let me see if I can put it out too. If you can read to me the question, that would be very helpful.
Yeah, it was just asking to find the intercept of the function -9 and then the square root x plus 2. Oh, sorry, not square root. It's just hold on, let me find the actual. Sorry, I was reading the wrong one.
Oh yeah, no problem. Take your time.
It was the exponential function. It was -19, and then the little x at the top, and plus 2, and it was just saying to find the plus 2 was actually just adding to the whole.
Okay.
Yeah. So it was just saying to find the new y-intercept. I was a little confused. I thought it was a different answer, but yeah, I just wanted to see if you could tell us.
Yep, no problem. That's a good question. So just double check the function is -19 raised to the power of x. 19 is a base. Is that correct?
Yes, this is after I did a few transformations onto it.
Okay. Okay, no problem. Good question.
Do you need the original function?
We can work with this. So this is a function we need to find the y-intercept of, right? let's see, this is the f of x, and then we need y-intercept. So if we just forget about the +2, if we just forget about the negative and just begin with f of x equals 19 to the x, so begin with y equals 19 to the x. Now 19 is a base, and the coefficient in front of 19 in this case just 1, doesn't have a number there, right? So that means this function, if we plot it quickly, it looks like this because b is 19 more than 1. So it's going to be exponential growth, and it's going to have this y-intercept. Suppose we don't know what it is. We can plug in x equals 0. If we put 0 there, 19 to the 0 give me 1. So the y-intercept is at y equals 1. So this y-intercept is a 1, 0. So y equals 19 to the x has y-intercept, sorry, not 1, 0, 0, 1, because x equals 0 here, y equals 1, right? And then if we think about, okay, what does the negative do, the negative sign does to this, what does the negative sign do to this 19 to the x function? Well, that negative sign is going to flip the function over the x-axis. So it's going to reflect over x-axis. And that's when we reflect this function over x-axis, we're going to end up with a graph below the x-axis. The 0, 1 will be reflected to 0, -1, right? So there's a new function, -19 to the x, is going to have y-intercept 0, -1. And there's a horizontal asymptote with those exponential functions. When we reflect over the x-axis, the horizontal asymptote stays on the x-axis, it doesn't move. But the next part, when we take this function and we add 2 to it, so the +2 at the very end means we're going to move it up 2 units. We take whatever we have, the blue curve, we're going to shift it up 2 units. If we do that, when we shift a graph up or down, the horizontal asymptote is going to move, so it's going to go up 2 units. So that's a 1, 2. So the horizontal asymptote now is here. And the y-intercept also going to move up 2 units. So that's a 0, -1 now if we move it up 2. So 1, 2. So now it's at this 0, 1. And if we draw the final graph, it looks probably something like this. So that's a -19 to the x +2. And from there, we can find out by just quickly sketching, we can figure out the y-intercept. It's going to be at 0, 2, right? Now let's see, we just don't want to sketch the graph. We just want to know, okay, what is a y-intercept? Not through transformations, but just looking at it, we want to know, right? And we can always begin with this function that we have up here, the f of x equals -19 to the x +2. And we want y-intercept, which means when we find the y-intercept, we know with lines, with quadratic functions, right, x has to be 0. So if we set x equals 0, put in there, so we get f of 0 equals -19 to the 0 +2. And then negative times 19 to the 0, which is -1, right? 19 to the 0 is 1, but the negative is still there. And the +2, so that gives us 1. So we get this as 0, 1 as the y-intercept. So I just want to show you 2 ways. One is we can think about transformations. The second way to find the y-intercept is literally just taking the x and set it equal to 0. Does that help?
Yeah, it does. Thank you so much. I just messed up the transformation, honestly.
Okay. Yeah, it's always a good practice to work with transformations, because a lot of functions, if we think about transformations, it makes a lot more sense. Like, oh, okay, that's how we get it, get to that point. But yeah, just I think be a little bit more careful. You should be okay.
Thank you so much.
Yeah, no problem. Good question. Any other questions? from homework or from study for the quiz? All right, I think a problem like this is going to be a fair question on the quiz, right? It asks you, okay, here's a exponential function. What kind of transformations does it take to get to this function from 19 to the x? What's the horizontal asymptote? What's the y-intercept? All of those questions are reasonable, I think, because they're all related to the graphs of exponential functions. All right, let's see. All right, any other questions before I begin with today's lecture with the new material? All right. Well, if you think about other questions, definitely let me know before the quiz. We can spend time on it. So for now, I'm going to begin with 4.6, solving exponential and logarithmic equation. So we're not talking about functions here. We're just going to work with a lot of equations. Excuse me. So the first example I have, so we're going to solve all those equations from now on. So the first example is 2 to the x equals 2 to the 3x minus 2. So if we have an example like this, the left side, we have an exponential expression with the x and the exponent. The right side, we also have this exponential expression. They're not the two expressions are different, but in this case, the base are the same. So same base. If the base are the same, so what we do is we're just going to make sure that the exponents are the same, right? Because we have these two expressions, they equal to each other. That means whatever the values we get when we plug in the x value, we must end up with the same value on both sides. Therefore, every part on the left side must equal to every part on the right side. And the base are already the same, the exponents have to be the same. So those two exponents must be the same. So we set the numerator x equal to 3x minus 2. And then we can just quickly solve for x minus x on both sides, plus 2 on both sides. So x minus x equals 0, plus 2 give me 2. And then 3x minus x is 2x. Now we divide by 2. So we get x equals 1. We can also check, right, if we take x equals 1 put in there, the left side, we get 2 to the first power. The right side, we get 2 to the 3 times 1 minus 2, which is also 2 to the first power. So we get 2 on both sides. All right, so that's how we solve the equation if we have the base are the same on both sides of the equation. Here's a second example. We have 2 to the 5x equals square root of 2. Now this problem looks like the left side is different from the right side if we just kind of quickly glancing at it. And the left side is exponential. The right side is just a number, square root of 2. How do we solve this? Suppose we don't have a calculator to use. Well, the trick here is that we're going to take a look at both sides to see if we can make sure the base are the same. So try to do some manipulation until the bases are the same. So make both sides same base. So the left side, we have a base 2. There's probably not much we can do there, but the right side, square root of 2, we can actually rewrite this using the exponential notation, the exponent notation. So that's 2 to the 1/2. So 2 to the 5x equals 2 to the 1/2. And now we kind of end up with the first example case, right? We have same base on both sides. We just make sure the exponents are the same. 5x equals 1/2. We just set those two exponents equal. to each other. Now we can solve for x. So we get x equals divided by 5 on both sides. Now 1/2 divided by 5 is kind of moving the 5 into the denominator. So that's x equals 1/10. Any questions? You probably think, okay, those examples are easy, which is true, they are easy. All right, so the next example I have is just getting a little bit more difficult because it's just a different form of the equation. It's a little bit different. So now we have 2 to the x equals -100. What is the x, right? Let's just see, for those problems, we don't have calculator to use, right? None of those problems, we could use a calculator. So how do we find the x? Well, normally, suppose, normally when we solve an equation like a 2 to the x, what we do is we can add log. We can either convert it to x to the logarithmic form, or we can add natural log or add log on both sides to bring the exponent to the front. But in this case, it's actually a lot more straightforward if we think about the graph of 2 to the x. So graph of 2 to the x, which is the exponential, kind of like the 19 to the x we had earlier. So it looks like this. This point is 0, 1, and it has a horizontal asymptote on the x-axis. And if you remember with exponential functions, we're either going to have exponential decay or exponential growth. In this case, we have this exponential growth. The a is 1, so this function is never going to be below the x-axis. It's always going to be above. So all the y values from 2 to the x is going to be positive. So it's impossible to have a negative number. So since 2 to the x is going to be positive for all x, so this means for all. So for all, upside down a means for all x. So we cannot have a negative y value from 2 to the x. So no solution. So 2 to the x don't equal to 100, never. So no solution in this case. Let's see, suppose we just don't know that, right? Let's just see, we have this example and this equation we need to solve, and we just don't think about the graph of 2 to the x. We just want to solve it as a normal equation. So what we could do is we could take, let's just say 2 to the x equals -100, right? We could convert it into log form. So convert to log. So what we have is we have base 2, so we got log base 2, and then in the equation that's next to the 2, now it goes to the other side, so that's an x. Away from 2 now actually goes into the log. So we got log base 2 of 100 equals x. If it's defined, then that's definitely true. But if you remember, long time ago, well, not long time ago, maybe last week when we talk about log functions, anything inside the log, so in that parentheses after log, right, it must be positive. So this term, whatever in there, must be positive. And now we have a negative number in there, therefore it's not going to be okay. We cannot have a log of a negative number. So if you end up with x equals log of 2 with a negative number inside, there's no such x. So no solution, because we cannot have a negative number. I just want to show you there's 2 ways to solve this, and maybe other ways too, but you either from the graph of 2 to the x or from the log function, the domain of log function, you can tell that there's no solution in this example. Okay, questions on this? All right, let's see. The next example I have is 3 times e to the 0.5t equals 11. And I don't have a calculator, which is fine. We're just probably going to leave the expression with logs or natural logs if we have to. But let's look at this example. So here we have 3 times a exponential function with a t in it. We're looking for t, right? Because that's the only variable we don't know here. That's equal to 11. So the first thing we're going to do is we're going to isolate the exponential part. So the 3, we don't want it there. We need to get rid of it by dividing by 3 on both sides. So we get e to the 0.5 to the t equals 11 over 3. Okay, what do we do now, right? Well, now what we can do is we can actually try to bring the t, kind of isolate the t out of the exponential part. So there's 2 ways. Again, I'm going to show you 2 ways. The first thing we're going to do, so this is method 1. The first thing we're going to do, we're going to convert to log. In this case, it's not really log, it's more like a natural log because we have a base e. But nevertheless, so let me write down. So we can write log base e, because base is e. And anything away from the base now goes into the log. That's 11 over 3. Anything next to the base in the beginning now goes away. So that's a 0.5 to the t. So that's how we get the t out of the exponential part, by going from an exponential equation to a logarithmic equation. And now we just rewrite the left side, which is the natural log. The log base e is natural log of 11 over 3. To make it easy, I'm going to rewrite 0.5t as 1/2 t. And just fractions are a little bit easier to work with in this point. And we're going to multiply by 2 on both sides to isolate the t. So if I multiply everything by 2, I'll multiply by 2 on both sides. So I get 2 natural log 11 over 3, which is equal to t. That's how we get t. And I don't have a calculator to use. This is perfectly acceptable answer. It's actually more accurate than the answer you get by plugging this into the calculator. Any questions on this method? And we can always double check, right? Inside the natural log, there's no negative numbers. It's a positive 11 over 3. That's perfectly fine. All right, so that's one way. Now the second way is, remember that I want to get the t out of the exponent, right? So here I have a e raised to 0.5t equals 11 over 3. Let me just rewrite that. E to the 0.5t equals 11 over 3. How do I get the exponent out of there? Well, what we do is we're going to get rid of the base. How do we get rid of the exponential base? We need a logarithmic base. So what I'm going to do is I'm going to add natural log on both sides of the equation. Basically adding log base e on both sides of the equation. And the natural log and the e, so let me rewrite down natural log with e to the 0.5t, that's the same thing as the log base e of e to the 0.5t, right? And log base e and the exponential base e, they cancel. So same thing, natural log and this base e, every time you see them together, you can just immediately cancel them. And what we end up with on the left side is just 0.5t remaining. And that's going to equal to natural log of 11 over 3. Again, to make it easier, the 0.5t, which is a 1/2 t, equals natural log 11 over 3. And we can multiply by 2 on both sides to get t equals 2 natural log 11 over 3. So the difference is really in this step to get the exponent out of that exponential expression, we add a logarithmic operation on both sides. So I just want to show you 2 ways. Eventually they are the same, but they just preference whether you want to convert it to logarithmic form or you just want to add a operation of log on both sides. Personally, once you get a feeling with this technique, the second method is seem to happen more naturally. Like when you see it as like, oh, I need to get rid of the base e, I'm going to add a log base e on both sides, natural log in this case. All right, questions on this? Awesome. All right, let me know if you have questions. So that's example 4. And the next example I have is it's a little bit more difficult because now we have 5 raised to the 2x minus minus 1 plus 1, it doesn't really matter that much. That's equal to 4 to the x. So here, what we have different from something we saw earlier, right? The first example, we have base 2 on both sides, same base. We just said the exponents equal. But here, the base are not the same. One is 5, one is 4. What do we do, right? Well, if we try to convert this into logs, it's actually more challenging because let's just say we want to convert this into logs. Let's say we pick the 5 there as a base. So we might write as log base 5 of something equals something, right? Now, what goes into the parentheses after the log? That's 4 to the x. What about the other side? 2x minus 1. Okay, so we still have an x in the log, then we have to use the property to bring the x in front. If you don't know that, you kind of get confused over here, right? So that's one way to do it. It works if you're familiar with the properties of logs. Now, I don't like to think in this way. What I like to do is I like to think, okay, I have base 5 and a base 4. I need to get something out of the exponent on both sides, not just one side. So what can I do to the equation so that I can get the exponents outside of that exponential expression? Well, that's where we use logs. So what I do with this example is I just take both sides and I use natural log all the time because I'm more comfortable with natural log. It also less writing. You can also use log base 10, log base 5, or log base 4, whichever you prefer, but I just keep it natural log. So if I add natural log to both sides, using the properties with the exponent. So if we have an exponent inside the log, that means that we can bring the exponent to the front. So in this case, we can bring both exponents to the front, in front of the logs. So now what do I have? I'm going to have 2x minus 1, that was the exponent, but now it's in front of the expression. So 2x minus 1 times natural log of 5 equals x times natural log of 4. You probably wonder, okay, that doesn't look good because we have 2 natural logs. Don't worry, natural log of 5 and the natural log of 4, they're just numbers. You have to think about them, they're numbers. They're really not some weird expression that we don't know. If we have a calculator or if we have a computer, we can get a really good estimate of those 2 numbers. So think about them as numbers. So those 2 are just numbers. Kind of think about them as like a square root of 2 or pi, they're just numbers like those 2. They're irrational numbers. So those are the numbers. Okay, how do we solve for x? The next thing what we're going to do is, because we have an x on the left, we have x on the right, and the x are being multiplied by numbers, it's really just a linear equation. Now, I want to point out that this equation here is not different from, so this one is not different from equations like, let's see, 2x minus 1 times 5, I'm not going to use 5, times 2 equals x times 3. So if I give you this equation, you know immediately what to do, right? You're going to bring the x to the same side, factoring, and then try to solve combined like terms and solve for x from here. Now, I want to show you that the one we got is exactly the same, except that instead of having a 2 here, we have a natural log of 5. Instead of having a 3, we get natural log of 4. We just leave them, but in our mind, we keep telling ourselves, okay, we just have numbers here. So we're going to do exactly the same thing we would do with the simple equation on the left. So what I'm going to do is I need to bring all the x together. On the left side, I'm going to distribute the natural log of 5 into the parentheses. I get 2x natural log of 5 minus natural log of 5, which is a number, equals x times natural log of 4. And now I'm going to bring the x terms to the same side, to the left side. I'm going to minus x natural log of 4 on both sides. It's really x times natural log of 4. And then I'm going to add natural log of 5. So to move the natural log of 5 to the right side, I'm going to add natural log of 5 on both sides. You know what? Let me take 2 steps. All right. So first of all, move the x natural log of 4 to the left. So I get 2x natural log of 5 minus x natural log of 4 minus natural log of 5 equals 0. And now I'm going to plus natural log of 5 on both sides. So I have x terms on the left. So I get 2x natural log of 5 minus x natural log of 4 equals natural log of 5 on the right side. Okay, so how do we solve for x? Well, we're just going to factor the x out of the 2 terms on the left. So get x times 2 natural log of 5 minus natural log of 4. That's equal to natural log of 5. And then we're going to divide by the parentheses because that's really a number. So this is, again, this is a number. And we're just going to divide by that number on both sides. We get x equals natural log of 5 divided by 2 natural log of 5 minus natural log of 4. And you probably wonder, can we simplify this? Sure, we could try to simplify this, but probably not a lot. We can try to simplify it, but it's not going to simplify too much because at some point we're going to end up with natural log of 5 divided by another natural log, and I'm just going to leave it the way it is. It doesn't look nice, but certainly that's just a number. It's nothing else. Any questions on this example? So that's what you do when you, well, that's one of the ways to solve problems when you have the base are different and then you have x in both parts. All right. Questions? All right. So if you don't have questions, I'm going to move on to the next example, which is similar to this one. So that next example is we have 2 times 5 to the x equals 3 to the x plus 2. Now, here you probably think, okay, what's a big deal? Just the left side multiplied by 2, the 2 base are still different. And then we have x in both exponents. Can we do the same thing by adding a natural log on both sides? Certainly we can do the same thing, but we have to be a little bit more careful here because the 2 times 5 to the x is a little bit different than what we had earlier with just one term. So if we add natural log on both sides, the left side, what we have is the product inside the log, right? So that's where we have to use the product property to break that apart. I'm going to use a different color, so be careful here. So when we break this apart using the product property, so we have natural log of a product equals the sum of 2 logs. We get natural log of 2 plus natural log of 5 to the x. Oops. And that's equal to the right-hand side, natural log of 3 to the x plus 2. So that's the very first step using the product property with logs. And then what we're going to do is we're going to, just like we did before, the natural log of 2, there's not much we can do. We're going to leave it. But the natural log of 5 to the x can go to the front of this log. X plus 2 can also go to the front of that log. So now we have natural log of 2 plus x times natural log of 5 equals x plus 2 times natural log of 3. Right? And then we can distribute the natural log of 3 into the parentheses on the right. So that's going to be, if we distribute natural log of 3 there, so we get x times natural log of 3, and then we have 2 positive 2 natural log of 3 with the multiplication. So now we just have 4 terms instead of 3. We get 2 x terms and the 2 terms without x. So when I combine like terms, so I'm going to subtract x natural log of 3 on both sides. And then I'm going to subtract natural log of 2 on both sides. So that way on the left side, I have x natural log of 5 minus x. So let me write down x natural log of 5 minus x natural log of 3 is equal to the right side. Remember, this goes away. This goes away. So we get 2 natural log of 3 minus natural log of 2. And on the left side, we have 2 x terms. We can pull out an x from there. So let's factor x from here. So we get natural log of 5 minus natural log of 3. The right side, I have this difference. So that's 2 natural log of 3 minus natural log of 2. If I want to solve for x, I'm going to have to divide by this parentheses on the left. So I get x equals 2 natural log of 3 minus natural log of 2 over natural log of 5 minus natural log of 3. This is perfectly fine to have. All right, any questions on this? Now, this is a very good example. I want to show you, just in case you wonder, okay, can I rewrite this answer, right? Yes, you can absolutely rewrite it. We can condense the logs. So the numerator, we have a difference of 2 logs. So I'm just going to rewrite this. The 2, if I want to rewrite the numerator, the 2 is going to go into the exponent of the 3. So we get natural log of 3 squared minus natural log of 2 divided by natural log of 5 minus natural log of 3. And in the numerator denominator, both are difference of logs. We can write them as quotient. So we get natural log of 9 over 2 in the numerator divided by natural log of 5 over 3. Right? And that doesn't look nice if you don't like fractions in the log, but to be honest, there's really no other option. You probably wonder, okay, so now I have a quotient of 2 logs. Can I rewrite them? You have to be very careful. If you have a division between 2 logs, the only way you can rewrite them is use the change of base formula. So that's going to become log base of 5 over 3. So the 5 over 3 in the denominator log, so that becomes the base. And then the numerator part, so 9/2, just going to go into the log. So that's how you write it using the change of base formula. But to be honest, I really don't expect that it's necessary to write into the single log form. I think this one is perfectly acceptable. Even the division on the left side is perfectly fine, just as good as the final condensed form. So it's not required. As long as you have one of the 3 forms of the answer, then you'll be fine. Okay, any questions on this? All right, I'm not hearing any questions. So in that case, let me move on to the next example. So this is 6. Oh, wait a minute, I lost track. So that's a 5. This is example 6. The next one is 7. So in this example, I have 3 plus e to the 2x equals 7 e to the 4x. Now here we have something a little bit more complicated because we have base e, right? We have two terms with e, and then we have exponents with x. But then we also have the 3 plus something. Now this one, we cannot get rid of the base because if we add a natural log on both sides, there's nothing we can do on the left. I just want to quickly show you, but I'm going to erase it in a minute. So if I just say, okay, I'm going to add natural log on both sides, there's no way to rewrite this. So cannot rewrite to separate the terms. There's nothing we can do except for just leave it the way it is. And it doesn't really help us because we get an x stuck in the log. So that's not going to be helpful. How do we solve this? Well, one way to solve it is using the calculator, plotting the function on the left, plot the function on the right, look for the intersection. In this particular example, what we can do is actually using a small substitution trick. Note that here we have e to the 2x, but here we have e to the 4x. And note e to the 4x is actually e to the 2x squared. Right? So what we're going to do is we're going to say, okay, we're going to let u equals e to the 2x, and I'm going to rewrite the equation above. So I get 3 plus u equals 7 u squared, because e to the 4x is u squared. And now we just end up with a quadratic equation we can solve. Either use the quadratic formula or factoring. And I don't really think we can factor in this case, in this example. So let's see, we're going to use quadratic formula, move every term to the same side. I get 7u squared minus u minus 3 equals 0. So u equals negative b, so negative negative 1 plus or minus square root of b squared minus 4 times 7 times negative 3 all over 2a, which is 7. So we get u equals negative negative 1 is positive 1 plus or minus square root of 1 squared. So that's a 1 plus 4 times 7 times 3. So 1 plus 4 times 7, 28 times 3. I think that's an 84 all over 14. So we got 1 plus or minus square root of 85 over 14. Okay, so the question is, how do we know which u it is? Do both u works? Well, let's go back to the beginning. Before we go back to the beginning, let's rewrite this answer too. So we get 1 plus square root of 85 over 14. And then we have u equals 1 minus square root of 85 over 14. So if you have a calculator, you can put both of them into the calculator and then get an estimation. If not, we're just going to leave it. But how do you know which u is actually the correct expression for e to the 2x? Well, this is sort of going back to the earlier problem we said. When we have u equals e to the 2x, then we know this must be positive because e to the 2x is kind of like an e to the x is the exponential growth function. It's never going to be negative. So the u cannot be the second one because this one is going to be a negative. And if you think about it, square root of 85 is some number probably close to 9 because 9 times 9 is 81, right? The square root of 85 is close to 9. 1 minus 9 is negative. So that's negative. So it cannot be the correct u. So the u has to be the first choice we had. Therefore, u equals e to the 2x is equal to 1 plus square root of 85 over 14. How do we get x from here? Suppose we still don't have a calculator. What we're going to do is we're just going to add natural log to both sides. So we get natural log of e to the 2x equals natural log of this complicated expression. And the left side, the natural log and the e cancels, give me 2x equals natural log 1 plus square root of 85 over 14. Now I'm going to divide by 2 to get x, so get x equals 1/2 natural log of 1 plus square root of 85 over 14. So that's what x is. But the trick is actually the beginning. I know that later on, with the square root, all those, it takes a lot longer to solve. But the trick is really the beginning, to recognize that you have 3 terms. You cannot just add a natural log or log to get the exponent out of there. But noticing that one of the term is actually the square of the other part of in a different term. So e to the 2x and the e to the 4x, the square of, e to the 4x is a square of e to the 2x. So noticing that, and then you can rewrite the equation as quadratic. All right, questions on this? Okay. Well, let me keep going and going over a few more examples, and I'll definitely keep an eye on the clock. Make sure you have a break and then enough time to take the quiz. All right. So the next example I have, this is 8 now. So we're going to solve this equation. It says 12 plus 2 natural log of x equals 20. All right, again, we're not going to use any calculator for this equation. We're just going to end up with whatever the expression we have. We don't even need to put it in the calculator. So while the x here is inside the natural log, right? So that means when we isolate, we're going to have to isolate this term at some point and then get the x out of there. So what we do is we first get rid of the 12. So 12 plus 2 natural logs. So we're going to minus 12 on both sides. So we get 2 natural log of x equals 20 minus 12 is 8. We need to continue to get rid of the 2. So divide by 2 on both sides. So we get natural log of x equals 4. Right? Okay, so what do we do from here? We need to get the x out of there. Well, there's a couple of things we could do. We could either go, this is a logarithmic, so we can convert this to exponential. When we want something out of the log, we convert it to exponential. When we want something out of the exponential, we can convert it to log. So if I convert this to exponential equation, this is the log base e, remember? So I have base e raised to some number equals something. So the 4 under the x will be switched place. So we switch the places of x and the 4. So we get e to the 4th power equals x. There you go. We have x equals e to the 4th power. That's the first method. You probably think, okay, that's really easy. Nice, right? But the second method, I still want to explain it to you how we get there, because sometimes it could be useful as well. So the second way to do it is to think, okay, so here I have a natural log of x equals 4. Natural log has a base e. So what I'm going to do is I'm going to take this both sides of the equation. I'm going to treat them as exponents with the same base. So I'm going to add a base e on both sides. So this is called adding a common base e. So if I add a base e to both sides, the left side I have e, base e in the exponential, and also natural log, which is a log base e. So this exponential base e and this logarithmic base, they cancel, give me x. So I get x equals e to the x. So both methods give me the correct expression for x. So it's up to you to take whichever approach you like that will make sense to you. Personally, I would say you can definitely convert it to exponential equation because that's what the definition is, using the relation between exponential and logarithmic. Or we can just think about, okay, here's a log, we need to get rid of it. We're just going to add a base e or whatever the base is on both sides. In this case, base e. So that's e to the fourth power, the solution. One thing I want to point out that we should check whenever we solve logarithmic equations, we always check. How do we check? We just take this, we're going to put into the original equation. So we get 12 plus 2 natural log of e to the fourth power equals 20. Now, the point of checking, obviously, to get the correct answer, right? But also to make sure that we don't have any extraneous solutions. Means we don't have any solutions. When we put in there, we get a problem. In this case, we're not going to have a problem because when we put e to the fourth power, it's a positive number, into the log, that's perfectly fine. So since e to the fourth power is positive, and the natural log of e to the fourth power is okay, it's good. And in fact, we can simplify the natural log with base e. So we get 12 plus 2 times 4 equals 20, which is true. But most important is to check, make sure the part inside the log is positive. All right, any questions about this example? Okay, the next example I have is example 9. So here I have 2 times natural log x plus 1 equals 10. All right, we got a 2 there. What do we do? Well, it's no big deal. If we have a 2, again, we're just going to get rid of the 2 by dividing by 2 on both sides. So we get natural log x plus 1 equals 5. And then we're going to do the same thing we did. So I'm going to use the second approach by adding a base e, because I have a natural log here. I'm going to add a base e to both sides. So I have base e natural log cancels. I get x plus 1 remaining, which is equal to e to the fifth power. And now I'm going to subtract 1. I get x equals e to the fifth power minus 1. Is that correct? Well, let's see. If I take this expression, put into the equation, I get 2 natural log e to the fifth minus 1 plus 1 equals 10. And it turns out that's true because this e to the fifth power minus 1 plus 1 is e to the fifth power. When we have a natural log of e to the fifth power, we just get 5. 2 times 5 equals 10. So yes, and then we don't have any negatives here. It's positive. Okay, questions? All right, if you don't have any questions, I'm going to move on to the next example. So the next example I have is, this is 10. So I have natural log of x squared equals natural log of, let's see, I have to change the problem a little bit to make it work. 2x minus 3. Well, okay, that's the equation, right? It's pretty nice equation because we have a log on each side. There's nothing else. It's pretty nice and clean. Okay, what do we do? Well, if we have a log and nothing else and the equal, so that means the parentheses part, they must equal. So we get x squared equals 2x minus 3. Oh, wait a minute. Do I want to be plus 3? I'm sorry, I think I want it to be positive. So let's change it to 2x plus 3 there. And then to solve for x, we're just going to move everything to the same side. So we get x squared minus 2x minus 3 equals 0. Perhaps we want to use quadratic formula or factoring. It looks like we might be able to factor here to save time. So that will be x, two numbers multiply give me -3. When we add, we get -2. So we get x minus 3, x plus 1. Okay, good. And then what we have here is we get x equals 3, x equals -1. So we get two x values. We have to make sure that we check both x values because sometimes one of them doesn't work. Sometimes both of them works. It depends. So here we're going to check. We're going to take 3, put in there. We get natural log of 9. Is that equal to natural log of 2 times 3 plus 3? Yes, because both parts are positive, right? So no problem. And then we get natural log of 9 on both sides. And now we check -1. So we get natural log of -1 squared. Is that equal to natural log of 2 times -1 plus 3? And it looks like we're fine. Because again, we get positive inside the natural log. That's positive. This is also +1. So both solutions works here. But again, be careful. Sometimes one of the solutions may not work. And a quick way to know that it doesn't work is when you put into the log, you get a negative value from the parentheses part. All right, the next example I have is, I'm almost done with those examples. The next example I have is log 3x minus 2 minus log 2 equals log x plus 4. So I have 3 logs, 2 on the left side, 1 on the right side, and then I have 2 logs with x in it, 1 on the left, 1 on the right. So what do I do? Well, if the trick here is that if we have multiple logs on the same side with the same base, obviously, we can bring them together by using one of the properties. So in this case, we have difference of 2 logs. So we're going to bring them together, use the quotient rule with logs. So that's going to be log, inside we get 3x minus 2 divided by 2. So that's how we combine those 2 logs. And then that's equal to log of x plus 4. And now we kind of have the case we've seen before with the logs. 1 log on each side, there's nothing else there, right? So what we can do is we're just going to set the inner part equals, we get 3x minus 2 over 2 equals x plus 4. So be very careful here. The first step, what we did is we combine those 2 logs into 1 log by using the quotient rule. And from here, we can actually solve for x. So if I multiply by 2 on both sides, so I get 3x minus 2 equals 2 times x plus 4. So that's equal to 2x plus 8. The left side, I have 3x minus 2. So if I minus 2x on both sides, and the plus 2 on both sides, so I get 3x minus 2x, so that the x equals 8 plus 2 is 10. So I get x equals 10. And to check, what we're going to do is we're just going to put x equals 10 into the equation. We get log of 3 times 10 minus 2. So that's 28 minus log of 2. Is that equal to log of 10 plus 4, 14? And this is the log of 28 minus log of 2 equals log of 14. It is, but more importantly, we have a positive number here and a positive number on the side in the log. So if you have a positive number in there, and chances that everything is going to work, you don't have to worry too much about not having a solution at the end. Okay, any questions on this example? All right. If you don't have questions, I have one more example here. Now, I just want to point out that, so let's see. Sometimes when we check, we get log of a negative number. So when we take the x value we put into the equation, we get a negative number inside the log. That's a problem. That's going to be the indicator that we have that whatever the x value we plug into the equation to check, that's not a solution. So the is not a solution. It's an extraneous solution. So that's just something to keep in mind, even though we are not seeing the examples here, but it doesn't mean it's not happening. All right, let me go over one more example before we take a break. The next example I have is natural log of x plus natural log of 3x is equal to 2. So here again, we have two logs on the left side, we get a number on the right side. What we do is we're going to combine the two logs. So we get natural log of x times 3x, so that's 3x squared, is equal to 2. And how do we get rid of the natural log? We have to add a base e or convert it to exponential. So I'm going to add a base e. So let me note. So be careful. From here, 3x squared does not equal to 2. So I know that some of us would like to kind of think, okay, can I just drop the natural log on the left and set it equal to 2? No. So 3x squared cannot equal to 2 in this case. So when we add a base e, we have e and the natural log goes away. So we get 3x squared equals e squared. Now we're going to divide by 3. We get x squared equals e squared over 3. And now we're going to take a square root on both sides. So we get x equals, if you remember, when we take a square root, we add plus minus. Plus or minus e squared over 3. So that's plus minus e times square root of 1/3. So that's a root 3 over 3. So we get plus or minus e times root 3 over 3. So here I have two x values. One is positive, one is negative, right? So let me write down, we get x equals positive e root 3 over 3. Even though it's not nice, I don't care, it's positive. And we have x equals negative e root 3 over 3. It's a negative. Okay, so let's take them, put into the equation, see if we have both x values being the solution. So if I put positive in there, so I get natural log of e to the root 3 over 3. Still, this is a positive, that's good. Plus natural log of 3 times e root 3 over 3. Again, this is a positive. That's equal to 2, positive. So that's equal to 2. That's good because inside the natural log, I get 2 positive numbers. Good. If we simplify, we should get correct the number 2. All right. So what about the so what about the negative? Well, when we take the negative x value put in there, so we get natural log of negative e to the root 3 over 3. That's a problem because this is negative. It's not okay to have a negative inside the natural log. So x equals negative e to the root 3 over 3 is not a solution. So the only solution we have is e to the root 3 over 3. All right, does that make sense? All right, I hope you have seen this before because, well, even if you haven't seen it before, I feel like you probably a little bit better prepared now when you see those problems. All right, it's 7:17. I think we need a break because I need a break. I'm sure you all need a break too. So when we come back, 7:18. All right, let's take a quick break. So come back at 7:25. Is that okay? So break until 7:25 p.m. All right, I'll see you in a few minutes. All right, hello, welcome back. So I'm going to go over a few more examples. Let's see, this is in section 4.7, exponential and log modeling. So we're going to look at some examples that's involving exponential and logarithmic functions. All right, the first example is doubling times. Now, just like the term says, doubling time, so we're looking for time. So what this means is that the time it takes to reach twice the initial amount. Time it takes to reach, twice of the starting value. Well, you probably think, okay, what is this really thing? Well, let me give you examples. So the question, suppose the unicorn population in Ireland doubles every 10 years. So what that's saying is that for the population of unicorns, if we're starting with some number and that number was going to reach twice that amount in 10 years. So the doubling time in this case is 10 years because it takes 10 years to reach twice of whatever the population it began with. So let's see, the population begins with 50. And what we're going to do is we're going to find a function that gives the population of unicorns after 2 years. So suppose we begin with 50 and the doubling time is 10 years, and we want to know, okay, what is a function that will give the population of unicorns after a number of years, t? So we need a function, and assuming the continuous grows, so the function is going to be a equals a of t, the population is equal to a naught, the initial population, e to the rt. Right? So we need to know what the growth rate is. We know the doubling time is 10 years, but we don't know what the continuous growth rate. We need to find it. But we're going to use the information that the doubling time is 10 years. So we're starting at 50, so we can put 50 into this equation first. So a of t equals 50, the initial value. So let me know that a of 0, remember this is the y-intercept or initial value, the starting value. So we get a of t equals 50 times e to the rt. And then we know after 10 years, the population is going to reach twice of the initial amount. So at t equals 10, the population is going to equal to 100, twice amount. So now we can put those two values into this function. So we get 100 equals 50 times e to the r times 10, t is 10. And we're going to solve for the exponential growth rate. So divide by 50 on both sides. We end up with 2 equals e to the r times 10 in the exponent. Now, I just want to point out that if we have a doubling time problem, we always end up with 2 equals e to the r with a t in the exponent, because whatever is the beginning amount, and then suppose we have the doubling time, and then when we put in the twice amount on the left, so we divide by the initial amount, we always have a 2. So now we can solve for r there by adding natural log on both sides. We get natural log of 2 equals natural log e to the r times 10. Natural log and the e cancels on the right-hand side. That's just going to be r times 10. So we get r equals natural log of 2 over 10. So that's the growth rate. It's a number. We don't have a calculator, so we can just leave it the way it is. Now we have the growth rate. We have the initial population. We can write down the function for population after 2 years. So a of t is equal to 50, the initial, times e, base e, and then in the exponent we have natural log of 2 over 10. This is the growth rate times time. So this function will give the population of unicorns after 2 years. But I want to point out that in this problem, what we did first is obviously we're going to begin with this exponential growth function. We have to find the rate first. The rate is not given. We're given the doubling time. So we find the rate, and then we put it back into the equation to write down the function. Okay, any questions on this example? So keep in mind that doubling time is the time. It's a time that it takes to reach twice of the starting value. So that's what doubling time refers to, is the time. Okay, the next example I have is related to half-life. Usually those examples are only related to decaying, exponential decay situations. So half-life is not a time. I know, even though when we talk about life means time, right? So half-life is actually, oh, well, let me take it back. What am I saying? Half-life is not half of what it is. It is also talk about the time. So half-life means the time it takes to reach half of the starting value. So again, just like the doubling time, the half-life is also referring to time. It just means, in this case, okay, how long does it take to reach half of the starting value? So for example, here's a question. The half-life of plutonium 244 is 80 million years. Which means it takes 80 million years to reach half of the value, half of the amount that we begin with. So find a function that gives the amount of plutonium 244 remaining after 2 years if we begin with A milligrams. So A is some constant. So suppose we begin with 8 milligrams, and we know the half-life is 80 million years, and we want to find a function that will give us the remaining amount after 2 years. Okay, so how we solve this? Well, in this case, we're going to assume it's exponential growth. Whenever we talk about half-life doubling time, we're always going to assume it's a continuous exponential growth. So we use the same formula, A of t equals A naught e to the RT. And we don't know the decay rate. And we have an initial value, which is lowercase a. We can use that. And we do have the half-life, which is the time, 80 million years. So we're just going to plug in those values. So let's see. We're going to plug in the initial value. So A of t equals lowercase a times e to the RT. And then we know that after 80 million years, we're going to reach half of that amount. So at t equals 80 million, the amount A of t is equal to half of this initial half of A. So we're going to take that number, put in there, put into this equation, we get half of the amount we begin with is equal to A times e to the RT is 80 million. And from here, we're just going to try to solve for the rate. So the A and the A, there's the A on both sides of the equation. So that cancels when we divide by A on both sides. So we get half equals e to the R times the half-life, 80 million. Now, in half-life problems, we always, at some point, we always end up with half equals something. Kind of like in the doubling time, we always end up with 2 equals some exponential. So that's always true. So from here, what we do, we add natural log on both sides. We get natural log of half equals natural log of e to the R and times 80 million in the exponent. The natural log and the e cancels, give us R times 80 million. So divide by 80 million, we get R equals natural log of 1/2 divided by 80 million. So that's the decay rate. And if we take that, put it into the function, we can write down the function for the remaining amount of plutonium-244. So that's A of t equals A, the initial amount, e to this rate, and then t. So I'm going to be a little bit lazy not to write down the entire expression, but the R there goes into the parentheses. Any questions on this example? Just be careful when you give a problem like this. Let's just say you look at it, you don't know what to do. Always begin with the exponential decay model of the general function for exponential decay, and then or exponential growth that's continuous, and then start with that and then plug in whatever we know, looking for any missing constants, the exponential growth rate or maybe the initial value, and then we should be all set. All right, here's the second example, or the third one, the second one of this half-life. It says a bone fragment that contains 20% of its original carbon-14 I'm sure you all know at this point that carbon-14 is also a exponential decay substance. So suppose carbon-14 has a half-life of 5,730 years. How old is the bone? So this bone, whatever the amount of carbon-14 it began with, right? After a number of years, only 20% of it remaining. We don't know how much it began. We only know that 20% of that amount is currently existing. And we do know that carbon-14 has a half-life of 5,730. We just want to know how many years has passed from the beginning of this bone. All right, so suppose I'm looking at it, I don't know what to do, right? So what I'm going to do is I'm going to begin with the exponential decay function. A of t equals a naught e to the RT. I don't know what the decay rate is. I don't know the initial amount, but I do know that the half-life of carbon-14 is 5,730. So I'm going to use that information to find the decay rate first. So use half-life to find decay rate. So I know that at t equals 5,730, the half-life, we know that the amount A of t is going to be half of what we begin with, A0. So take that expression, put into this function. So we get half A0 is equal to A0 e to the R times 5,730. And now we're going to divide by A0. So we get 1/2 equals E raised to the R times 5,730. Now I'm going to add natural log on both sides. So I get natural log of 1/2 equals natural log of base ER to the 5,730. That cancels. Give me rate times 5,730. And I can get the exponential decay rate. R equals natural log of 1/2 divided by 5,730. So that's the exponential decay rate. I have it now, so I can put into the function. So I get A of t equals A naught. The initial amount, again, I don't know exactly how much that is, but it's probably not going to affect how we're going to solve the problem. But let's continue. So that's E raised to the natural log of 1/2 divided by 5,730. So that's all in the exponent times t. So that will be the function that will give us the remaining amount of carbon-14 in the bone. And that's what we're going to use to finish this problem. So the problem says, at this point, the bone fragment only contains 20% of the initial carbon-14. We don't know what time it is, but we need to figure out the t, because that's what we want to know, how old the bone is. Okay, so we do know that at this point. So now we know that A of t is equal to 20% of the original amount. So that's a 0.2 times A naught. So that's how much we have carbon-14 now. So we're going to take this, put into the function above. So we got 0.2 A naught equals A naught e to the natural log 1/2 divided by 5,730 times t, and divide by A naught, or A0. So we get 0.2 equals this exponential expression, natural log of 1/2 divided by 5,730 t. And how do we solve for t? Well, just like we did before, right? We solved for the rate. Now we're just going to add natural log on both sides. This cancels. So we get natural log of 0.2 equals the natural log of 1/2 divided by 5,730 t. And we're solving for the t here. So we're going to multiply by 5,730 on both sides. So we get 5,730 times natural log of 0.2. Oops. That's equal to natural log of 1/2 t. And then I'm going to divide by natural log of 1/2. So we get t equals 5,730 natural log 0.2 divided by natural log of 1/2. And I'm not even going to bother to simplify, so that will be my answer for time. So that's how many years has passed since the bone was, well, since the bone existed. So that's how old the bone is. We really just end up solving the same equation twice, but for different variables. The first time we solve it, we solve for the rate in the exponent. The second time we solve it, we solve for the time in the exponent. All right, any questions about this problem? Let's see. All right, looks like okay, it's 7:47. Let's see what we're gonna do next. I have more examples. Let's see, 7:47. All right, I think I'm going to stop here. We still have plenty of time to cover whatever we need to cover before the exam. So I'm going to stop here. There's a couple examples. I don't have time to go over them now, but I'll go over them at the beginning of Wednesday's class. And then we're going to talk about other material that we need to cover. All right, on that note, well, let me stop. And any questions about today's class? Any questions about the quiz that you're going to take today? All right, so I'm not hearing any questions. Just a reminder that the quiz, just like all other quizzes, you cannot use a calculator, so the rule is the same. Let's see. No calculator, textbook, no online resources, or talking to someone else. None of this is allowed. Okay. And then again, just make sure that when you submit your answers, it's one PDF. It could have multiple pages. And let's say you have your work on 3 different pages, right, in your notebook. When you scan them and then when you submit them, make sure double check you have all the pages submitted. Don't just scan one page and submit that one page. Make sure that after you click on submit, you should be able to review what you submitted. Just double check, make sure that all pages are uploaded. All right, let's see. All right, any other questions before the quiz?
I have one comment, but it can wait till after.
Okay. Okay. All right. Let's see. Anyone else have any questions or comments? All right. It's 7:50. I think that gives us plenty time to take the quiz. I don't expect that you're going to spend 40 minutes on it. So on that note, let me make the quiz available to you. So just like before, make sure you submit your quiz before 8:40. So, you need to keep an eye on the clock, right? By 8:30, you should think, okay, I need to scan them now. That way you have enough time. So just make sure that you submit the quiz in time before it locks, before the quiz get locked, then you wouldn't be able to submit it. All right. If you have extended time and I receive your recommendation letters, if the letter says you have more time, then you have more time. If the letter doesn't say it, that's a different situation. Okay. But I think you all should be able to submit it in time today. I don't think the quiz is going to take too long, but do your best. And just like before, you don't have to stay here. Okay, I just published the quiz. Can someone open it and then let me know you can access it? You can open the quiz through Pages. And I think you can also open it through assignments. If not, just go to Pages.
We can access it.
Okay, awesome. Thank you. All right, good luck, everyone. You don't, like I said, you don't have to stay here.
Thanks.
All right, good luck. See you Wednesday.
And I submitted my test through the comments section of the submission.
Yeah, the exam, right?
Yeah.
Yes, I received it. Don't worry, I have not graded yet. I have not
All
graded.
right. I more just wanted to let you know, just in case you graded all the rest and like something went wrong. More just wanted to let you know.
Right. Yep.
All right.
Okay.
Thank you.
Yep. No problem. Good luck on the quiz. So you have more time. I think I put 9 o'clock.
Yep. I should be good to go. Thank you.
All right. Good luck.
Thank you.
Yep. Bye-bye.
Good night.
Yep. You too. Bye-bye.